Well, thanks. I'm very grateful for the audience and for Linda's publicity. It's true that the contributions of my research group have been honored, but I'm not exactly a climate scientist. My interest is the carbon cycle. And this just tells you a little bit about where I came from. I was in the Sputnik generation, and we entered college in 1958, and okay, we're going to select a group and put you in a so-called honors program, which turned out to be a license to more or less mangle your education. I wrote a senior thesis, for example, comparing the 20th century novel in the United States and Great Britain. It was the most supremely sophomoric thing you could imagine. And my advisor said, well, Mr. Hayes, I notice you've taken a lot of chemistry. I think you should pursue that interest. It's an absolutely true story. And I went into chemistry and loved it and slid into the earth sciences. And my principal interest has always been the carbon cycle, which, as you can imagine, turned out to be good luck in the decades that I was trying to raise research funds. The carbon cycle became the flavor of the second half of the 20th century, if you were looking for research money. And better yet, if you were looking for good students. So I studied that, and I have been worried about the carbon cycle, and it is related to climate change. And I think that's the sort of hook that Linda was trying to pick up, and I just hope that it'll be useful. What I want to talk about is the really basic stuff about the greenhouse effect first. I have the impression that lay people in general understand the importance, don't doubt the reality, but don't understand exactly how it works. And my experience with students generally is that when you understand the nuts and bolts, it takes on a whole new level of reality for you. And so I'm going to start out by talking about the nuts and bolts. And it's an energy balance problem. And so then the question is, what happens to the energy? And the key point is that it doesn't just warm us up. It changes the whole global circulation and what we call climate, rather than just the temperature. These processes have been going on as long as we've had an Earth and a sun. And so there's a history to this that is, I would say, largely irrelevant, except that it serves as a source of confusion. And I'd like to try to clarify that. And then there's a separate question, which we may or may not get to. It's absolutely related, but it's fundamentally separate, and that's the acidification of the ocean. So those are the points that come up. Why do I say it's an energy balance problem? Well, here is my highly artistic rendition of the sun and the earth. We are practically a kettle sitting on a stove, constantly receiving energy from the sun. I mean, we understand that in our guts. Here comes the sunlight. Put on a dark jacket and walk around on a sunny day, and you feel it. Since we receive that energy, we would be constantly warming up unless we balance the budget by emitting energy, which indeed we do. Every physical body radiates electromagnetic radiation. The range of wavelengths in which we radiate that radiation depends on our temperature. If you're the sun at something like 6,000 degrees Kelvin, who knows what the temperature is in the inside, but the photosphere that is sending radiation out from the sun is about 6,000 degrees Kelvin effectively. If you're that hot, you're white hot. And as you cool down, you go to red hot and stuff like that. If you're the Earth, which is around 285 degrees Kelvin, that means like 12 degrees Celsius, you're radiating as well, but at much longer, invisible wavelengths. The Earth radiates in the infrared. So we have here a body that's sending out visible radiation, and here's the Earth, which is emitting infrared radiation in order to balance the budget. And when we mess with the atmosphere, we are holding back that emission of radiation from the solid Earth. And as we hold back more of it, that's the nub of the problem. So I want to talk about how we hold it back. First of all, here's a picture of what's incoming. All right? This is power, watts per square meter on the vertical axis. And here's wavelength. This is a spectrum. The visible wavelengths are right in this range right here. And if the sun were exactly a 5,250 degrees centigrade, which is about, what, 5,500 Kelvin, black body, this would be its emission spectrum. What you actually see if you take a satellite up to the top of the atmosphere and look at the sun is this yellow figure. And what we get at sea level is what's shown here in red. The difference is radiation that's scattered in the atmosphere and partly reflected back into space. And here in the infrared region of the solar spectrum, there are big bites taken out of it by the absorption of energy by water. This absorption of energy, infrared energy in particular, by molecules is what plays an even bigger role when you talk about the emission of radiation from the Earth. Here again is energy on the vertical axis and wavelength on the horizontal axis. And this is this difference I was talking about, how the range of wavelengths at which you emit depends on your temperature. So here at short wavelengths, this is the sun radiating. Considerably longer wavelengths, here's where the Earth is radiating. At short wavelengths, the atmosphere is pretty much transparent. Nitrogen, oxygen, then, light goes right through them, no problem. Argon, light goes right through, no problem. At longer wavelengths, in the infrared, where the Earth is trying to balance the energy budget, energy is being absorbed by molecules, in particular by their chemical bonds. So here's a little molecular physics. Here's a water molecule, H2O. It sits there with these bonds to the hydrogen atoms vibrating. those bonds will absorb electromagnetic energy, provided, if and only if, that motion changes the magnetic dipole moment of the molecule. And as you can see, the overall average dipole is a positive charge out in this direction, a negative charge in that direction. The hydrogens tend to be positive. The oxygen, bristling with electrons, tends to be negative. So when that molecule does this, the dipole moment changes and water soaks up infrared radiation fabulously. No problem at all. CO2, on the other side, is a linear molecule. Again, the oxygens are negative and the positive is the carbon. And if that molecule sits there and just does this, there's no change in the magnetic dipole because the charge locations move complementarily and balance each other continuously. So that mode of vibration in CO2 is nothing to worry about. It doesn't filter out any infrared radiation. But there are other ways that CO2 can wiggle. And here they are. First of all, this is the so-called symmetric stretch. Spectroscopists sit around and they talk about the symmetric stretch and the asymmetric stretch and the out-of-plane bending, all this kind of business. But anyway, this is the one we just talked about. Here's an asymmetric stretch where the molecule's doing this. And if it does this, the dipole moment changes. And by the way, this involves the CO bonds, very strong bonds. So that absorbs like crazy in the infrared. Then there's this one, bending, where the molecule's just doing this, the carbons and the oxygens. That again changes the magnetic dipole. So this mode also absorbs infrared radiation. And this one is dangerous. That V2 mode occurs right in the middle of the range of radiation emitted by the Earth as we're trying to balance the budget. So what I have on the bottom here is a graph of the infrared absorption spectrum of a CO2 molecule. V2, that's this bending, comes where it really hurts, right in the middle of the Earth infrared emission spectrum. V3, which could be even more damaging, happens to come where there's not much radiation trying to get out anyway. So it doesn't matter much, that one. And these are overtones. They actually take a little bit, as we saw on an earlier slide, out of the solar spectrum. Any questions so far? Does it make sense? Okay? Do you feel better? I hope. Yeah. It's the CO2 molecule remains intact. It's just sitting there shaken. And when I shine an infrared photon on this molecule and it picks up extra energy, it goes from doing this to doing this, and then it relaxes back to the ground state by bumping into other CO2 molecules, which transfers energy to the atmosphere at large. And that's either heat or motion, which is the next point. Yeah. The point I'm trying to make, thank you. The things we're talking about are absolutely fundamental characteristics of a CO2 molecule. The molecule doesn't decide whether it's going to absorb radiation or not. It does it. I mean, a dye molecule, which absorbs energy in the visible range, it doesn't change colors. It always absorbs energy. It's always that color. This is the same phenomenon out at longer wavelengths, the CO2 molecule is always going to absorb energy. And this is the root of the scientific certainty about the greenhouse effect. You know, if you're putting more infrared absorbing molecules into the atmosphere, that energy is being deposited in the atmosphere. There are no two ways around it. The only question is, what happens to that energy? What does it do? It might warm us up, it might do something else. But there is utterly no question, you put in more absorbing molecules, more energy is going to be in the atmosphere. Sorry?
Because it's absorbing the energy instead of letting it.
It's absorbing energy that's coming upward from the surface of the Earth. People have worked out very detailed budgets about energy coming in and energy going out, and we can measure it. I'll show you this, but then I want to move, well, sorry, let me go right ahead. This is what you see if you take a satellite up above the atmosphere and you look back at the Earth and ask the question, what's actually coming up? This is out of a research paper, so don't get too worried. The top frame is looking down at the Sahara Desert, which is hot. So the black body radiation curve from that part of the Earth peaks out at about 320 degrees Kelvin, nearly 50 Celsius, really, really hot. That's the effective emitting temperature. And if the radiation were escaping unimpeded, we would see this smooth curve. But what you see when you look is there are these big bites taken out of the energy coming up. And here's a huge one. This is that V2 bending bands from CO2, taking out this huge chunk of energy. So everything underneath this curve represents energy, and the part that's not making it up to the top of the atmosphere represents energy that's being soaked up in the atmosphere. And it's unbalancing, or it's impeding the balance and holding energy into the atmosphere, making it harder to balance the budget by radiating energy out into space. This curve is from over the Mediterranean, a little bit cooler, quite a bit cooler, 280 Kelvin, but again, you see the same things eaten out of it. This is over Antarctica. It's so cold, it doesn't look like a big problem, but there is still that absorption there. If I go back, here's what it looks like overall. This is the spectrum that the Earth would emit if the atmosphere were comprised, let's say, exclusively of argon or some other noble gas that didn't absorb any radiation. But the fact that we've got CO2 and water and methane means that these chunks that are represented by yellow are being absorbed in the atmosphere. That's always been going on, of course. There's nothing new about that. We've had all of those gases in the atmosphere for billions of years. The only problem is we're putting in more CO2 in particular. And as that raises the temperature, it, by the way, raises the amount of water, because you increase the temperature of the sea at its surface, and you increase humidity, which increases the amount of water. It's a feedback that makes things worse as you go along. So, what are the effects of the absorption of energy? If you think about irradiating with sunlight a planet, a sphere, sitting where we are, and you imagine, just for the sake of argument, that that planet wasn't rotating. It was a shell of gas around a rock that was just sitting there. Well, the highest input of energy is going to be right at the equator. And up at the top, the radiation comes in at such an oblique angle that the amount of energy per square meter of surface up here is much lower. It means, big surprise, it's warmer at the equator and cooler at the top. That's going to drive circulation because at the equator, the warm air will be rising, and at the poles, the cold air will be sinking. And you'll wind up with a circulation about like this, if the planet's not spinning, if it's just a shell of gas around a stationary planet. But the Earth is rotating. This is the speed at Earth's surface due to the rotational motion. And here's the speedometer on the bottom. If you imagine that we could somehow completely disconnect the atmosphere from the planet so that the planet was spinning inside a stationary shell of gas, and you now held your hand out at the equator, you would encounter a wind of 1,037 miles per hour. That's the rotational speed of the planet. But of course, the atmosphere is frictionally bound to the planet. So the atmosphere, the shell of gas, spins along with the planet. But this imposes all kinds of forces. Imagine you're one of those sinking gas molecules up at the equator, and up the North Pole, and you're coming down, and as you're descending and as you're heading back toward the equator, the planet's spinning underneath you. So your pathway changes, and this is what you've probably heard of, the Coriolis Effect. This is what the Coriolis Effect is trying to explain, that you've got this turning planet underneath this gas shell. And the effect of this is that the very simple single circulation cell that you would expect in each hemisphere is just totally stirred up by the effects of the planetary rotation. And it breaks up roughly into 3 bands. Instead of just this one earlier, we saw gas rising at the equator, going all the way up to the pole, and coming back down. And what I'm saying now is that when you start spinning the planet, the turbulence induced is such that you wind up with it getting only to about 30 degrees before it just sinks anyway. And so you have these cells, typically 3 major bands, which define these things you keep hearing about, the trade winds, the prevailing westerlies, and the polar front. And this is obviously, if you ever watch TV weather, not something that stays put. We hear about the polar vortex wandering all the way down. This 30-degree marker, for example, is roughly the southern border of the United States, right? That's 30 degrees north latitude. 60 degrees north latitude is right underneath the curve of the Gulf of Alaska and through Stockholm and Norway, those parts of the world. So there's a lot of territory up here that has this circulating gas in it as well. And last winter we heard about the polar vortex sneaking down into Minnesota. So it was like 20 degrees out of place in terms of where it usually sits. But the energy that we see, or that's being absorbed, is what drives this circulation in the atmosphere, and as well the circulation in the ocean. I mean, we haven't even thought about that yet. The ocean is sitting there, and it's a fluid, it can move, and it's experiencing all kinds of gravitational forces that are strongly modified by the shapes of the ocean basins. And so to calculate how the ocean is moving around is a major problem. This is what people call geophysical fluid dynamics. And if you ask me, it makes nuclear physics look simple. It's a very, very difficult problem to calculate all of the effects, all of the forces that are driving these circulating fluids at Earth's surface, the ocean, and the atmosphere, and in particular, their interaction. So a huge portion of the energy goes not into warming, but instead to modifying, disturbing, enhancing, suppressing aspects of this circulation, which is to say, the energy goes into changing climate. And this is of huge consequence to our economic welfare and everything else. We can try to figure out more about what's going on. Here's what I just said. Absorbed energy affects climate, weather, as well as temperature. The problem is we can't go back and get weather reports, but we can estimate temperature retrospectively. For the past, oh boy, this is 20,000 years. There have been glacial cycles. So here is the LGM, is the last glacial maximum about 20,000 years ago. There are multiple ways we can quantitatively estimate the temperature as long as we've got ice. So that we've got ice up to about 800,000 years age on Antarctica. And there are indicators in the ice, the hydrogen isotopes in the ice cores give us a very good indication of temperature retrospectively. And we can thereby notice repeated glacial cycles back to about 1 million years ago. And you can look and see these things were periodic. And this is one of the straws grasped by people who say, well, look, this kind of variation in temperature is nothing new. It's been observed before. Absolutely true. There have been large variations, and they have been natural. And they've even, many of them, as you can see, been quite rapid, at least on a geologic time scale. So here's 1 million years, and you can count, what? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Yeah, that's right. About 13 ice ages numbered systematically through the past 1 million years. You can work back farther and estimate temperatures from oxygen isotopes in limestone shells, actually all the way back to at least the Cretaceous Tertiary boundary, and see there were times when it was really warm with palm trees growing in Antarctica and at high northern latitudes. So it has been much warmer in the past. You go back still farther, and these temperatures back to 550 million years ago are estimated from carbon cycle models and are much less secure. But we can certainly see that there has been a lot of variation in the past. And very interestingly, that for a good chunk of recent history, it's been periodic. And this is an interesting question. Why was it so stinking periodic? And this was worked out by Milutin Milankovic, a Serbian astronomer and physicist, who was fascinated by evidence literally dating from Egyptian times, bearing on the tilt of the Earth's axis. The Earth's axis, right now, it inclines 23.44 degrees relative to the plane of the ecliptic. It goes back and forth between about 22 and 25. Just back and forth a little bit. And the time scale, it's a periodic change in the obliquity. It's about 41,000 year cycle. But there are other changes. Jupiter and Saturn, orbiting beyond the Earth's orbit, affect the Earth gravitationally, and they change Earth's orbit so that sometimes it's perfectly circular and sometimes it's more elliptical. And so this goes back and forth like this. And that's a cycle of about 400,000 years. And finally, like any spinning top, the Earth wobbles. It precesses like a spinning top, and that's a cycle of about 21,000 years. Those things all affect the distribution of energy on the surface of the planet. The total energy depends on the sun. But as these orbital variations take place, the distribution of energy on the surface of the planet varies, and the distribution of energy throughout the year changes. And Milankovitch worked out the conditions that led to, or that favored, accumulation of ice. And he recognized that the key point was how much energy was being received in the northern latitudes around 65 degrees north, because that's where you've got both cold and dry land that will sustain and support ice. If you put ice on the ocean, it gets warmed up by the underlying waters, it can move around, it's not very stable. If you put ice on the continent and you have a cool summer, then that ice will tend to survive and you can build ice caps. So Milankovitch hypothesized that when you had minimal insolation, minimal reception of sunlight, or slightly less, let's put it that way, at northern latitudes, you had accumulation of ice caps. And he recognized that the periodicity was about right. Those three effects, the eccentricity, the tilt, and the precession, you can add them up and come up. This is what Milankovitch did. By the way, part of the time while he was imprisoned during World War I, he amused himself in his cell by working out efficient methods of calculation, paper and pencil, to do this and figure out how energy varied at these northern latitudes. And he came up with this now iconic estimate of the variation in solar energy received at about 65 degrees north. And then you look at the growth and decay of the ice caps, and the correlation jumps out at you. So everybody said, this guy's right. The major driver on these periodic ice ages has been so-called Milankovitch cyclicity. It doesn't turn out when you get, it looked really good between the First and Second World War. The evidence was so fuzzy that the precision and the match